Thanks, Frederick, and thanks to the organizing committee for giving this opportunity to speak here. So about myself, we are working in this space of waste management for almost a decade now. My background is more into process design and development, and what Venus shared on the last slide at EIL, yes, I worked for EIL for some time, and before moving to Australia. And recently, I just came back in the month of July. We are working on all the kind of waste like plastic waste, e-waste, and we are hearing on these kind of waste for last 1.5 days, right? We have a big project on RDF, your municipal solid waste, as well as on tire waste with Department of Commerce and Industry. But this subject is pretty close to me because it is coming from me in a way and from all of us. So on a lighter note, my daughter always says to me that, Baba, are you making something out of poop? And that's what we're talking over here. So biosolids is an upcoming problem in India. Globally, yes, been already people are handling in Europe. A lot of companies are there in Europe and Australia who have already commercialized technologies. But we are still at TRL, I think, 3 and 4. So you can always search their technology, like Pyrage is there in Europe, who has commercialized it and getting a CAGR of almost 14%. Pyrocal is in Australia. And we are developing one technology in Australia, PyroCo. I'll briefly mention about that. So biosolids, moving forward, please, is a kind of sludge, wastewater sludge, which you all know, how to treat wastewater. This is a big picture that wastewater treatment is a stage-wise process through mechanical separation, physical separation, and biological separation stages. Then you reduce the moisture in it using this multi-plate screw press dewatering units to around 20% because the solid content is very low in the initial feedstock. It is 2 to 3% or maximum 5%. So you bring it closer to 20%, and then you further dry the feedstock to get the sludge turd. So you have different technologies for drying operations, which needs energy ultimately. Moving forward, please. So about the biosolids types and contaminants, I'll give you a very high-level information that there are different types of biosolids. Again, it's a fecal sludge, or you can say the sludge coming from industrial wastewater. So you can get it in the pelletized form or the lime amended or the composted form. But the big picture is that, or you can digest or you can have that AD process and then get the biosolids from it. The big picture says that the energy content in the feedstock is between 12 to 20 megajoule per kg with the average solids content of around 20-25%. Now you have to bring it closer to 85% of solids to use it for any energy recovery application. And I think Vinu mentioned briefly about that moisture content part. So there are different drying operations available globally in the market. We are working with one industry who are working on the low temperature dryers because drying needs significant amount of energy because of the evaporation, latent heat of evaporation, as we know. So there are direct dryers and indirect dryers. Definitely we can speak about it later after the session because of the time paucity. The major contaminants, as you can see, other than the nutrient value in biosolids, so commercially in India, we are getting around 120,000 tons per day of fecal sludge. Out of that, only 40% is being managed properly. 60% is going to the water bodies, is being dumped illegally, you can say in a way, and it's causing a lot of contamination. So what kind of contamination we are talking over here? Definitely pathogens are one of those. Heavy metals, which are coming with the industrial wastewater like arsenic, cadmium, other than zinc and copper. Can you extract them? That's one thing. So we are talking about resource recovery other than the energy value. The functional groups are there, which maybe some of them may create some problem for the water bodies or the aquatic life. The major issues in the current time globally, which people are focusing on, is PFAS, other than polyaromatic hydrocarbons, PHs. PFAS is per and polyfluoroalkyl substances, just for your information I'm telling you. The maximum allowable limit in soil as per to EPA. I'm telling you, this is the data, PAH and for PFAS. Because PFAS comes from the firefighting foams as well as from your household stuffs like Teflon. If it is going in the water bodies, it's ultimately coming to your food chain when you are throwing that biosolids after drying to the any land side. So how to treat this kind of waste? Please to the next slide. I always talk to my industry partner about the thermal upcycling technologies. Yeah, keep on moving. People do compare technologies. Yes, it's good to compare, but it totally depends on the type of feedstock which you're having. What is your requirement? Are you focusing on the energy value, or are you looking for the resource recovery? It's up to you. Moving, keep on rolling. Yeah. So there are three primary technologies which I've compared over here. Definitely there are other two. So pyrolysis, gasification, and combustion. That's a big picture. People always say that you are working on combustion, you are talking on pyrolysis. Which one is better? All subsets. You have to choose which technology you have to work upon. And I think a lot of experts in this room knows about all these technologies. I won't speak too much. But my understanding is you can select a technology based on your feedstock quality, based on your scale of operation, and what exactly you are looking for, what product value you are looking for. Moving forward, please. So yeah, as you can see, pyrolysis gives you, other than the energy value, some resources also, which is being termed as biochar, or the char value. Then from gasification, you get the gasified char with lower carbon content, and the energy value in the form of syngas. And combustion is all about the heat energy. So you have to look which is the sweet spot for you to work. So currently we are focusing on pyrolysis operations because our interest is in the resource recovery, basically in the form of char value. Can you move forward, please? Yeah, so that's again your biosolids upcycling work which we are doing in our campus. So we have a different scale of operations starting from 5 to 10 kg per hour scale to 50 kg per hour scale in our lab. And now currently we are scaling up to 1 ton per day facility using one of the funding from DST for capacity building in waste to resources of 10 crores. Here, as you can see, that we have used the fecal sludge available nearby Jaipur region and converted into biochar as well as some energy value. So we are focusing both on the oil value and the gas which we are generating. But the major emphasis, as you can see, is on the char, because char we are using, because now it's free of pathogens, we have already treated at around 500 degrees Celsius. And you're using the char for the agriculture application. So as you can see, there is 50% increase in the seedling growth. We are working on the mustard plant, along with 20% of enhancement in the initial chlorophyll content, which is a significant value as per to our requirements. So you can see some analysis has been done for the product as well as for the feed, and that is a basis to design the process, to select the operating conditions, and to scale up the process. So as you can see, biochar, you can find application in agriculture as well as non-agriculture applications. So there are some low-hanging fruits, there are some high-hanging fruits which you are interested into. Moving forward, please. These are some of the major non-agriculture applications of biochar. The nutrient recovery, as a catalyst you can use, as an adsorbent you can use, and the market value varies significantly. As an additive in the rubber sector, I'll show you one case study. So in rubber, you use it as a partial replacement for carbon black. And 1 ton of carbon black releases 2 tons of carbon dioxide during production from fossil fuels. So there's a significant removal of carbon dioxide from the atmosphere. Then as a secondary fuel, definitely we can use, it's a low-end application and a low-hanging fruit. And the smart energy systems, mainly for developing batteries. That's another biochar to batteries project on which we are currently working. Moving forward, please. You need certain properties of biochar, which you can, so we can basically engineer biochar in our labs by modification of the surfaces for the desired applications. So that's another angle which we are currently exploring. Moving forward, please. So that's a big picture, as you can see, for rubber compounding application. That's a very big market. If you're going to look at the carbon black market, it's growing at a very significant pace. And as you can see, that the requirement only in India is close to 1 million ton per annum. 20% of that goes to rubber sector, the low-end rubber, and around 60% goes to tire sector, which is high-grade rubber, you can say. So these are some of the results which we have started with the participation of one of our industry partner, of replacing carbon black, which is coming in the rubber as an additive for increasing the mechanical strength. And what we have noticed that when you are looking for 100% replacement, it is not giving you that good results because of the impurities present in the biochar, like the metal content. But when you go for partial replacement, those results I haven't discussed over here because of some patent issues. But around 5 to 10% of that carbon black you can replace with this biochar. So the twofold advantage is, could you just remain at the previous slide? Okay, fine. So 5 to 10 replacement, you can imagine, like, we are talking about 1 million ton requirement. 20% of that is around 200,000 tons of carbon black, which is going to the rubber sector only. And 5 to 10% replacement, we can talk in terms of 10,000 tons, which is basically eliminating 20,000 tons of carbon dioxide from your atmosphere. Is a significant number. Plus, it will fetch you a value of close to $1,000 per ton. Then construction applications, we already tried it as an additive to cement. It is giving us some very good results by 1% replacement of biochar over there. And that is another way to store your carbon. So the point here is, like, is a multifold benefits we are looking for. One is the energy recovery. Second is basically your carbon value and the carbon storage. So carbon value in terms of replacement of carbon black or any additive in the cement sector, which is again a low-hanging application for us. And the fire clay bricks and the plaster, I think, what I can see it properly from here. But whatever replacement you are making, it's to store the carbon in that material for very long, because it's all fixed carbon. It is not gonna evolve into the atmosphere.
Abhishek,
yeah. Sure. Moving forward very quickly, some high-end applications, production of sustainable carbon nanomaterial from wastewater sludge for internal applications. Keep on rolling. So this is again a big picture. We are talking about CNMs and the hydrogen value from the sludge as part of the circular solution. We are producing carbon nanomaterial, this is one of the projects which is going on in Australia and RMIT, and I'm part of that project. And CNM is costing around $3,000 to $7,000 per ton. With hydrogen, which is, we can say is a fuel value for you. Moving forward, please. Keep on rolling, please. Frederick is very particular about time. Please move on. Integrate carbon nanomaterial coated biochar and hydrogen production from biogas and biosolids. Keep on rolling. So you can use biogas, which is coming from the wastewater treatment plant from the AD processes, to get your carbon value. So you can decompose your biogas in presence of biochar as a catalyst. You can use your biochar as a carbo-catalyst and then get your carbon precursors, which is mostly in form of carbon nanospheres. And then use that carbon nanospheres in the same industries for removal of PFAS as well as H2S, in the AD process. So you can see some of the results of that work. It is that flow sheet is being shown over here. You can use that carbon nanomaterial to remove PFAS from your water. And then you can see that PFAS concentration has dropped down significantly from 310 to close to 50. And it is comparable to activated carbon, GAC, which is market value is quite high. So that's again a circular solution we are looking over here. Please, just to the last slide. So thank you with that. And that's what you are seeing over here is we have developed a solution, a low-cost, environmental friendly solution to remove heavy metals. Because as I was mentioning in the beginning, heavy metals which are available in biosolids is causing a trouble for the land application. So if you're going to remove it in the first place, you can send it back to the metallurgy industry. So it's a resource recovery at that front, as well as it will improve the biosolids properties for biochar applications. So this is again like, two birds in one swipe. Thank you very much. And, the best way to move forward is collaboration.